is, can you see my screen now?
G.
Okay. So this is what we can say. This is all about the problem which I have received. So that is how to find the dimensional formula of kinetic energy and of the potential energy. So first we will talk about that. We will find the methods and how to prove that the kinetic energy is equal to half mv square. Am I audible? Hello.
J. J.
Okay, if you can audible, if I am audible to you, so you must have the pen and paper also. That
Yes.
at least you should write the main points of this lesson. And this was a question number 7 of your exercise. So that
G.
was the kinetic energy half mv square. So let's see how can we find its dimension and how can we prove that the k is equal to half mv square with the help of dimension. So first let's see if my screen is visible to you. So I am just going to display the next, that is the kinetic energy. Please, if you can read, please read this one.
Kinetic energy can be defined as the energy possessed by the body by virtue of its motion.
It's motion. So it's energy which is possessed by a body by virtue of its motion. If some body is moving, it is in motion, and definitely it must have some energy. Due to this movement, that energy is called the kinetic energy of the body. So it's a very simple definition. So after defining that, the mathematical equation is, you can see that mathematically we can write Ke for the kinetic energy. It's a half m multiplied by this x is for the multiplication. So v square, v is the velocity. So from here we can say that m is the mass of the body and v is the velocity and the square of that. And this is the 1 by 2 of this whole quantity. So now our problem is that we are just going to find the dimensions of all these quantities. So first of all, we'll have to see, if you are just looking at the right hand side, so we have m. M is for the mass, and you know that the dimension of mass is m. Similarly, there is a velocity. So velocity involves two things. One is the displacement and the second is time. The rate of change of displacement is called velocity, and that is a scale. So after understanding this formula, now we are just going to put the values. So you can see the dimensional formula of mass. As mass is involved, so first is half m. So we are looking for the dimensions of m. So that is m1, L0, T0. What I mean to say, m is the, what we can say, that is the quantity, that is mass, the quantity of matter, and its power is 1 because mass is all alone. So we will have to keep this formula all the time in mind, that half m into v square. So here we are putting the formula just to find out the dimension. So first we are talking about the mass, this m. So m is, its dimension of mass is m1 lt. So basically there are three dimensions, m, l, t, because we are talking about the basic quantities. So basic units, m is for what? M is for mass. And L is for what? Length, or you can say distance, displacement, or between the 2 points. And what is T?
Time period.
It's a time in seconds. So MKS. So here we can say that mass, and this is a distance. So in mass there is no distance involved, no length is involved, no time is involved. So that's why I am just writing all these basic dimensions but putting the power 0. So anything power 0 is 1. T is 0. So that's a power is 0, 1, 1. So 1 is nothing. So we have only m. So m is for the mass because its dimension is m, which is what we can say that m is describing the mass. The dimension of the mass is capital M, and it is involved in the formula only one time. So that's why we are putting the power 1 to it. So L and T, these are not present in mass, so that's why their power is 0. So after defining the dimensional formula of mass, we are just moving to the next part, that is the dimensional formula of velocity. The next factor is velocity. As we know that half mv square, so velocity is the next. So in velocity, there is no mass. So that's why the dimension of m is raised to power 0. Because we are writing all three basic dimensions, but here m is not involved. So we are just putting the power 0 to m. So this will become 1, nothing more or less than that. L is involved. What we can say, velocity is the formula is d over t. So d is the displacement. So once again, displacement is the length. So length can be measured in L. Its dimension is capital L, and it's a d over t. So d is involved only one time. So L is coming with the power 1. And this t is because it's a division, that rate of change with respect to time in the displacement. So this d over t. So d is the displacement, that is the length. That's why we are putting L or over t. So this t is coming over there in the numerator. So that's why its power is negative. Once again, t is only once. Are you getting this? Is there any?
Yes.
Because this t is negative. Why it is negative? The question is why it is negative. L is positive, t power is negative. So what is the reason?
Because t was in because t was getting divided
in the denominator. In the denominator, because as per the definition, the simple answer is as per the definition of the velocity, it is the rate of change of displacement. So rate of change means d over t, the displacement over the total time. So that's why t is over here in the denominator, but in dimensions, we will have to bring it in what we can say without any fractional format. So that's why this t is becoming negative, having the power 1. So because and then in what we can say velocity, displacement and time is only once. So displacement is represented by L and time is t, and this negative as per the formula because it is the ratio of. So we have written the dimension of mass, and now we have just written the dimension of velocity. So let's see if we are putting the values in the equation. So our equation is kinetic energy, as we know that half m into this x is for the multiplication sign, v square. So v is the velocity of that moving body. So half mv square is a very famous formula. So this formula is for the kinetic energy. So that's why we are just going to put the dimension m, capital M for the mass, and is multiplied v, velocity. We have just noted that t, that is L t minus. So we are just going to put those dimension in this equation of the kinetic energy. Now let's see how that left hand side as it is, that is Ke, and this is the dimension of mass, as we know that m1, and this is L0, T0, nothing more or less than this. This is 0, means nothing. So x, this is the multiplication sign, and once again this is a velocity square. So dimension of velocity was this in the last step, and square mean that is as per the formula of kinetic energy. So there must be the square of velocity. So what we have done over here, we are just putting the dimensional formula putting the dimensions in the given equation. Now let's see. It will become just like that. M1 LT. Now this and this square was over here, and this time this square is coming inside. What I mean to say that when you are putting 2, so M0 is nothing doing with that. So L will become square, and T that was -1, and this square is coming over here. We are giving the power square to each and every dimension of our formula. So that's why V square is this, dimension of V is this. So L2 and T -2 is over here. So I am sure that you are with me. You are getting this. Is there any confusion? Is there any confusion? So you can ask,
No.
you can, okay. Anyhow, we are just going to the next step. That is the last step. So dimensional formula of kinetic energy is, so everything power 0 is nothing. So we are not mentioning over here. So that's why we are getting the most simplified format of the dimension of kinetic energy. So this is all about the dimension of the kinetic energy. I'm sure that you got this one, but it's a question was just like that we will have to prove that whether it is right or wrong. So I will share that what we can say, what I received the screenshot of that. So let me just share it. So if I can get that, so it's somewhere over here in the WhatsApp. Anyhow, so this was the problem. This was I received. So that was show that. So this was show that mean that we will have to prove this one. And the second part is about the potential energy. So we have started from the right hand side. That was half mv square, and we have proved this one. But anyhow, if we are just going back to our slideshow, so one more thing is that I'm just going to share that was the what we can say, that was this format. So this was what we can say. So this was I'm sure that you can see my screen. Is there
Yes.
Oh, okay, let me share it. Oh yes, this one. So this was my whiteboard. So I'm sharing over here. So now you can see my sharing. So this was the question number 7 of your exercise. Show that. So till now we have proved that the right hand side of mv square, its dimension, and that dimension is what we can say, that is m l square t minus 2. Am I right? That was the last step, the dimension of that. But anyhow, if we are just going to share what we were talking about, that, so that was the this one, that is okay. This is the actual the second next part is, so let me share the previous one that was about the kinetic energy. So this is all about that. So this was the what we can say, the slideshow, and we reached over here. That is if I can just this one. So we were putting the values. Now from here, this was the dimension formula, what we can say, of the kinetic energy, and we have proved this putting in the equation. So let's see, this was the dimension, half mv square. Now you can ask the question, where is 1/2? If you are not asking, so let me ask, where is 1/2? Because in the original format there was k is equal to half mv square, but when we are writing its dimension formula, there is no 1/2. Is there any answer? Where is 1/2? Because in the original format we have, you can see now, this was 1/2. Okay, but when we are writing the dimensional formula, this is the equation, this is the formula in mathematical form. But after getting all those dimension of each and everything, we are ending over here. So this is the dimensional formula of kinetic energy, that is m1 l square t minus 2. Where is 1/2? Actually, 1 by 2 is a constant. But I mean to say 1 by 2 is a constant number. That is 1 by 2 everywhere. There is no change in 1 by 2. So whenever there is a constant number, that may be any digit, fractional number, any negative or positive number, or any particular value of any constant, so that will not affect on the dimension of that quantity. So there is no function of that constant, because dimensions are not concerning about the constant. These dimensions are only for the variable things. But we can say, we can change the value of m, we can change the value of v, the velocity. So the energy, kinetic energy, is depending upon all the variables. If the mass is greater, you will get the greater kinetic energy. If it is moving at the greater speed or velocity, so once again you will get the greater quantity of kinetic energy of the body. So I'm sure that now you are crystal clear that why we are not taking 1 by 2 in the whole process. Am I right?
जी.
So I'm sure that you got that 1 by 2 is all of a sudden there is no 1 by 2 in the dimensional formula, because 1 by 2 is a constant, and in the dimensional formula, in the dimension of anything, constant is not affecting anything. So we are just considering the variable. So this was the what we can say right hand side. But if you are just looking to the left hand side, that was now we are starting from the left hand side. What I mean to say, that this was the unit of the formula is that System International. The unit of kinetic energy is Joule. And what is the definition of Joule? Joule is the unit of work. And as you know, that energy is the ability to do work. So to do work, we will have to define the work. So what is work? Work is the product of force and the distance. Am I right? Work is what?
जी.
Work is what? How can we define the work? Work is the product of distance, force, and distance. If some force is acting on a body and it is converting a distance, then we can say the work has been done. So Joule is the unit of kinetic energy, because kinetic energy is the ability to do work, and work is the product of mass, force into distance. So Joule. So left hand side is just like that. Look at this, Joule. So Joule is Newton per meter. Newton is the force, meter is the distance or displacement. If we are applying a force F, so its unit is Newton, and it under the influence of applied force, if somebody is moving to the distance m meter, so it will definitely, the work has been done. So Joule is now Newton. What is Newton? So Newton is the force. Newton is the force applied to a body, and under that influence, if it is moving 1 meter in 1 second in a unit time, that is called 1 Newton. So this is the definition of Newton. If a force is applied on a body and it moves, what we can say, the force. Now Newton is force, and you know that force is F/m. So once again, F is the force, that is m is in kilograms, and A is what we can say the square of the, what we can say, the rate of change of the acceleration, and this m is over here. Now Newton is defined that if a force is applied and it produces an acceleration of 1 meter per second square in that body, that force is called 1 Newton. In the most simplified format, that if we are applying a force, under the influence of that force, if there is the acceleration of 1 meter per second in that body, then that quantity of force is called 1 Newton. So that's why this Newton is defined in this way, that mass in kilogram, and there is the acceleration F is equal to ma. As you know that F is equal to ma. Alright, ma. Look at this. Let me write over here that if the F force is defined as F is equal to ma. And you know that m is kilogram mass, so a is the acceleration. So a is this one and m is in kilogram this. So this m is over here. So we are just proving the left hand side, Joule, kinetic energy. So that's why this is for the force and this is for the acceleration. So this will become 1 Newton. Because Newton can be defined as the force which produces 1 meter acceleration, 1 meter per second acceleration in the body. So this is called the Newton. So that's why we are defining this force in this way. So anyhow, this was all the explanation of this. So let's see. The next is, so Joule, that is denoted by J, and kilogram mass per second, and this ma, F is equal to ma. Now the next is Joule, and as you know, the capital M is for the mass, L square, and T. So this is the acceleration, and what we can say, this is actually the mass and acceleration square. So force, and this is the displacement L2, and T has the definition of acceleration. So that's why kinetic energy is m for mass, L square, and T minus 2. So from here we can say the left hand side is equal to right hand side. The right hand side we have calculated the formula with the help of the formula of kinetic energy. Both are same. So I think that this has been done now. Is there any query about that?
No.
Okay. Because kilogram, as you know, that m and m square over s, when we are multiplying the second m with that. So that is m for the kilogram, and then m square over s. So in this way we can get the dimension of, what I mean to say, that is the dimension of kinetic energy. And this was what we can say the proof of that. The both the homogeneity of the equation is that left hand side must be equal to the right hand side. Now let's see. So this is all about this one, and one more part is that is just we are going to prove the potential energy on the same lines. So that was PE. Let me check it. That what was that? So this was, I'm just sharing that screenshot, that this was. The B part is that potential energy, and small g mean that is gravitational potential energy is equal to mgh. So our line of action will remain the same. But I mean to say that if we are just going to do this one, so we will have to write in this way, that if I am sharing this one, so from here we can say that let me check this. So look at this, that if the potential energy, can you see my board? Let me share it.
No.
You are not showing. So let me share this one. So first is this what we can say, this was my board. So this, now let me check it, that this was the problem. This was the screenshot. So we are just going to solve the second part, that is the B part, that potential energy, gravitational small g is representing the potential, gravitational potential energy, that is mgh. So for that we are just writing in this way. This was that potential energy. I'm sure that now my whiteboard is visible to you.
Yes.
Okay, now let's see if we are writing in this way. Let me check my pen. So here this was, so PE is equal to mgh. So if we are starting from the right hand side, so right, we are looking for the dimensional formula of this. So right hand side is m, g and h. So here we can say that m is kilogram, that is the mass, and g is once again the gravitational pull, that is the velocity, rate of velocity, that is v, and then we can say that is the time factor is also involved, that is of the scale. So this was just like that. So let me show first the slides, then you will be in a better position to understand that. So that is the potential energy. So now you can see this one. Are you looking my screen?
Yes.
How to calculate? Let me starting from the first screen, that is how to find the dimensional formula of potential energy. So this is exactly on the same lines. We will have to write the right hand side and we'll put the formula, put the dimension of each and every variable involved that. So let's see. So that is the kinetic energy. Please, if you can read my slide, please read it.
Kinetic energy,
yes,
defined
can be
energy
defined
by the body by virtue of its position.
By virtue of its position. So its configuration or position is the same, that when it is placed somewhere at some height, so that definitely it will possess some energy, the ability to do some work, that is called the energy, due to position, due to the under the influence of gravitational force. Mathematically, formula is this one. This is the basic formula, that potential energy PE, mass m, g, gravitational acceleration small g, and altitude, that is h. So mgh, this is the formula of potential energy. So we'll put the dimensions. So dimensional formula of mass is, as you know, that is m1, and the other two quantities will become 0, having 0 powers. And next is g. So dimensional formula of gravitational acceleration is m is 0, there is no mass, and l is the dimension, that is the displacement, that is the distance, and this t is twice as a negative, because the acceleration, gravitational acceleration is there. So acceleration is always time defined as time square. So meter per second square, we can say meter per second square. So per second square is coming in this way because it is the rate of change of velocity, and velocity is also the rate of change of displacement. When there are two rates with respect to the same variable time, so we can put it, what we can say, that is the time dimension. Okay, that's why twice. Now dimension formula of altitude. Altitude mean that is the height. So height is once again L, only the displacement in upward direction. So that's why the T and M is 0. When we are putting the values in the equation, so P, M, G, H. So M is M1 and that was Mg. G is just like that, and L, one more L is coming from the height. So that was L T minus 2, that is the gravitational acceleration, and one more H is coming and making it square, LT square. So what we can say, this was the right hand side. Dimensional formula of this just like this one, and this will be converted into this, and then finally we have the dimension of this. So I will send all these slides at the end, so don't worry about that. So next is, we are starting from the left hand side. The system international unit of potential energy is Joule. So once again, the Joule can be defined as Newton meter, and Newton meter can be defined in this way. So we are putting the dimensions of all these quantities, kilogram, and the time, and the meter, what we can say, the length. So this is the mass, this is the dimension, what I mean to say, the distance, and this is the time factor. So once again, from the left hand side, the potential energy as per the formula is this one. So left hand side and right hand side is equal. So what we can say, this is all about the formula, dimensions of all these. I hope that you understand each and everything. Is there any query?
No.
Okay, if you understood all this, so you can write in your own, and I will send also these slides, and if further query, you can ask that. So I am just going to what we can say, once again I'm relogging it for Azwar to solve his problems. So let's see, just going to end this one, and then we will have to be logged again. I will send the ID once again, WhatsApp. I will WhatsApp you. So we are just going to end this meeting.